Hello, welcome to the graphical user interface walkthrough for the next generational sequencing with the Burrows Wheeler Transform comps project. My name is AJ Rustino, and I'll be providing a guided overview of our project using this GUI as a visual aid. Any and all project resources are available for download through our GitHub, and our essay detailing our research can be found attached on this website. Without any further ado, I'll skip the table of contents so we can begin with an overview of the subject of our project, the Burrows Wheeler Transform. As mentioned previously, the focal point of our project is the string compression preparation algorithm known as the Burrows Wheeler Transform. On this slide, and the ones following, we'll provide clarification on the encoding methodology, functionality, and application of the Burrows Wheeler Transform in short read alignment. To begin to understand our project, allow me to introduce the BWT. In function, it's a rotational string transformation algorithm with interesting and useful mathematical properties. Invented in 1984 by David Wheeler and Michael Burrows, its original purpose was to prepare long text for traditional compression methods, such as run-length encoding, or RLE for short. On screen you'll see two strings, banana and its corresponding code word, which we affectionately call ANBA. But the real question is, how do we get from banana to ANBA? The BWT encoding process begins by adding a sentinel character to the end of the string. In most instances of BWT encoding, the $sign is used. The character is integral to the encoding and decoding process, generally needing to have a lexicographical or alphabetical priority greater than that of all other characters in the input string. After we add the sentinel character, we build a table of cyclic rotations. What I mean by this is you move the sentinel character one letter to the right, maintaining the order of characters in the string. The result of this, as seen below number 2, is a table of cyclically rotated strings characterized by the diagonal movement of the sentinel character. Next, we lexicographically order these rotations. In other words, alphabetically sort them. That's step 3. Finally, we take the last character of each of the lexicographically ordered strings. This is our code word, ANBA. Having the code word is great, but what if we'd like to decode it? Before I go into the actual methodology by which the BWT code word is decoded, let's first take a look at why it's possible to fully decode a BWT code word using just the word itself. The answer to why this is possible is a principle called last-first ordering. The easiest way to understand this is to look at the first and last columns of our lexicographically ordered rotated strings. As seen on screen, the order in which the characters appear on the right, in the code word, is the same order they appear in the first column. This is to say the numeration of the characters distinguishing them from each other is unique. Those are the exact same characters, just in different rotational positions. This is very much an overview of this concept. Be sure to see the mathematics, algorithm, and methods sections of our paper for more info. However, the concept of last-first ordering informs the theory upon which BWT's involvement in next-generational sequencing as a whole came to light. More to come in later slides. For now, let's look into the practical decoding I mentioned earlier. To decode a BWT code word, all you need is the code word itself. Starting off with a lexicographically sorted code word, we add a second code word that is not sorted to the first, making a table of 2 character strings for each letter in the code word. After this, we lexicographically sort our new strings. Lastly, we repeat this process until we have completely reconstructed the original table from our encoding. The decoded word is in the row with the string ending with our sentinel character, the $sign. All we have to do is return it from the table, and like so, we have our decoded string. This is the basic tenet by which the BWT works. Next, we'll talk about how this factors into next-generational sequencing. Since the late 2000s, the BWT found an additional use in the field of genomics in aiding with genome mapping through next-generation sequencing, or NGS for short. We'll talk about NGS in the following slide, but for now, NGS can be thought of as a black box that outputs a series of characters, 4 specific ones, A, C, T, and G, the base nucleotide pairs of all DNA sequences. These sequences can vary in length, up to millions of nucleotides per sequence. This is where the BWT's compressibility comes into play. As mentioned earlier, the BWT is meant to prepare text for run-length encoding, RLE, a method of compression that encodes runs of similar characters using numbers that indicate how many duplicates of the same character occur in a row. On a small scale, RLE is not that effective. Take our code word ANBA, for instance. Using RLE on it actually creates a larger string than we already have. However, NGS returns massive strings of only 4 characters. In other words, the perfect setup for RLE. Notice how, when we encode the example base pair string, and then run RLE on it, the resultant compression is 8 characters shorter. Imagine this in the scale of an entire genome, the smallest of which, as mentioned in the second paragraph, consists of 159,662 characters. The meat and potatoes of NGS is that it's a method by which fragmented half DNA strands are synthesized using labeled A, C, T, and G bases. then matched onto a location or multiple locations on a labeled and pre-built complementary half strand spanning potentially hundreds of thousands, if not millions of characters. This is the process by which all modern genome models are mapped. For an example of how this might work, see the example provided on screen. Feeding both the small and large strings into an alignment tool, the alignment tool returns the matched location. On the slide, the substring is also visually aligned to its correct location, something we chose to implement in our own C-based alignment tool, available through our GitHub. Before moving on, let's address the theory behind BWT's involvement in NGS regarding last-first ordering. Two Italian scientists created a data structure called the FM index, named after themselves, Faragina and Manzini, consisting of two tables. The tables themselves take longer to build with larger inputs, but permit nonlinear scaling of looking up substrings as matches on a larger string. In other words, the size of the input dictates the time it takes to build the table, but not the speed of table lookup. For more info on this, see the math and algorithms section of our paper. But for the sake of this presentation, this is the how as to BWT's role in revolutionizing genomics.
Insofar as I use the term revolutionize, I'm referring to the invention of BWT-based short-read sequence aligners, or SRAs, in the early 2000s. The first of these tools was Bowtie, a 2008 program which preceded BWA and SOAP2 in 2009. Prior to the invention of these software packages, MAQ, spelled M-A-Q, was the dominant SRA in genomics. It doesn't take a close look at the figure to understand why the BWT was so revolutionary to the field of genomics. Look no further than Note 1 on processing time. Irrespective of which aligner you choose, the processing times of all three are multiple orders of magnitude smaller than MAQ across the board. The BWT-based aligners weren't perfect at their inception and have come a long way since 2009. This is most noticeable through the confidence and error metrics being on average lower and higher respectively for the BWT-based aligners when compared to MAQ's performance. This is all to emphasize that the BWT isn't a perfect solution. It's what it did to the outputs and processing times of NGS that made it a cornerstone of genomics. The compressibility we discussed earlier, combined with the speed at which genes can be mapped, has resulted in genome models becoming more accessible than at any other point in history. More easily mapped, stored, and shared, genomes of all types have experienced a paradigm shift in representation, for better or for worse. After all is said and done, there's much more to this project than I have covered in this guided overview. There are algorithm enhancements, mathematical analysis, and an entire suite of ethical concerns we've uncovered throughout this project. To fully experience the combined effort of all 6 members of this project, as well as our own advisor, we implore you to explore the materials attached to this GUI and website. To conclude, on behalf of the BWT Comps Group, we would like to formally thank Professor Layla Esper of the Computer Science Department at Carleton College for her continued support and excellent leadership in this project, as well as the Computer Science Department for their accessibility and engagement with our group. Thank you.